right, so ready to dive into methane removal.
Always.
We've got this research paper here from January 2025.
Oh.
And
oh, yeah, I saw that one.
it's a lot.
Yeah, it's not exactly light reading.
No.
But don't worry. That's what we're here for.
That's right.
So this paper digs into ways to remove methane from the atmosphere.
Yeah, and the really interesting thing is that it focuses on enhancing a natural process.
Okay.
Using chlorine atoms to break down that methane.
Okay, so chlorine atoms.
Mm-hmm.
And that's already happening. Yeah, it happens naturally, but at really low levels.
Okay, and so this is intriguing because it could be a faster way to combat warming than tackling CO2 alone.
Potentially, yeah.
Which is what we hear so much about.
Right, exactly.
And get this, they're talking about maybe integrating this with existing industrial processes.
Yeah, isn't that wild?
Who knew the chlor-alkali industry could be our climate saviors?
Right.
So let's break this down.
Okay.
First, why is methane such a problem?
Oh, it's a big one.
And then we'll explore this whole chlorine atom solution.
Yeah.
And then finally look at,
the real world stuff.
Yeah, the real world costs and feasibility of all this.
Exactly.
So, first, methane. Why is it the problem child of greenhouse gases?
Well, you see, its global warming potential is 84 times that of CO2 over a 20-year period.
84 times.
Yeah, it's a lot.
Much higher than CO2.
Much more potent, and since pre-industrial times, atmospheric methane has more than doubled.
More than doubled.
Yeah.
Wow.
It's gone from about 715 parts per billion to almost 1,900 today.
That's a big jump.
Yeah, a huge jump.
Yeah. And the natural sinks that usually help remove methane, things like soil and certain chemical reactions in the atmosphere,
right,
they're just not keeping up.
So nature can't bail us out this time.
Nope, this one's on us.
So this means we need active methane removal to hit those climate goals we keep hearing about.
If we want to make a dent, yeah.
Okay, so what are some of the existing methane removal methods and why aren't they enough? Well, there are a few options out there.
Okay.
One is thermal-catalytic oxidation, but that requires really high temperatures, so it's really energy intensive and could be pretty expensive.
So, not ideal.
Not really. Then there's photocatalytic oxidation, which uses light to trigger the chemical reaction.
Okay.
It's promising, but the efficiency is still an issue.
Got it.
And scientists are looking into ways to enhance the natural sink using hydroxyl radicals.
Okay.
But that research is still pretty early.
So nothing's really ready for prime time yet.
Not quite.
Okay, so the chlorine atom solution, this is where it gets interesting.
It does.
So remind me why chlorine is better.
Well, atomic chlorine breaks down methane way faster than those hydroxyl radicals we were talking about.
Okay.
Like 16 times faster.
16 times?
Yeah.
Wow, that's impressive.
It is. And, like we said, it occurs naturally, but just not enough to really make a difference.
Okay.
So this paper proposes a two-step artificial process to boost it.
Okay, break it down for me.
So first they would use electrolysis of salt water to produce chlorine gas.
Okay.
And then step 2 is photolysis, which is using UV light.
Okay.
Ideally LEDs to break down that chlorine gas and release all those powerful chlorine atoms.
Okay, so we're harnessing the power of light to destroy methane.
Pretty much.
Where would we even deploy something like this?
Well, they're suggesting two main scenarios.
Okay.
First, point sources like landfills and coal mines.
Okay.
Those could use smaller contained systems.
Like targeted methane removal?
Yeah, and then for large-scale atmospheric removal,
Okay.
they're talking about integrating this process with existing chlor-alkali plants.
So basically turning those plants into methane-eating machines.
Yeah, exactly.
That's pretty wild.
It is.
But location would be key, right?
Oh, absolutely. They specifically talk about coastal regions because they have access to seawater for electrolysis and the alkaline environment that you need to neutralize the hydrochloric acid byproduct.
Right. We don't want to create another problem while solving this one.
Exactly.
Got to think about those unintended consequences.
This all sounds great in theory, but how realistic is it from a cost perspective?
Well, that's the million-dollar question, isn't it?
Right.
And the researchers actually did some number crunching.
Okay, so spill the beans. What did they find?
Get this. Their estimates suggest that it might actually be competitive with some existing CO2 capture technology.
Hold on, are you saying this could be affordable?
Potentially, yeah.
Wow.
Even factoring in all the production costs.
I mean, CO2 capture is notoriously expensive.
Exactly. And it gets even better. Integrating with those chlor-alkali plants could mean even bigger cost savings.
Why is that?
Well, think about it. Those plants already have the infrastructure in place for electrolysis.
Right.
So you're basically skipping a huge chunk of the initial investment.
Ah, so we're repurposing what's already there.
Exactly. And there's another bonus. They wouldn't need to purify the chlorine gas for commercial sale,
Oh, I see.
which saves even more money.
So we're turning these industrial plants into double-duty climate heroes. Exactly. They'd be producing valuable chemicals and helping clean up the planet at the same time.
Okay, I'm really liking where this is going.
Right.
But before we get too carried away, let's back up for a second.
Sure.
I'm still a little fuzzy on how this two-step process actually works.
Yeah.
Let's break it down, starting with electrolysis.
All right, so electrolysis is basically using electricity to split water molecules into hydrogen and oxygen.
Right.
But in this case, we're using salt water, so we get chlorine gas as a byproduct.
So it's like a bonus ingredient.
Exactly. And the cool thing is this electrolysis process is already widely used in the chlor-alkali industry.
Right, to make chlorine for all sorts of things.
Yeah, swimming pools, PVC pipes, you name it.
It's kind of amazing to think that something we associate with keeping our pools clean could also help fight climate change.
It really is a full circle moment.
Okay, so we've got our chlorine gas from electrolysis now onto step 2, the light show.
All right, so this is where it gets really interesting.
Tell me more.
So we take that chlorine gas and we use ultraviolet light to break those chlorine molecules apart.
Okay.
And that releases those super reactive chlorine atoms we've been talking about.
And those are the ones that go after the methane.
They react with the methane molecules and break them down into less harmful substances.
Okay. Starting to get the picture now. Why LEDs specifically?
Well, LEDs are way more energy efficient than other types of UV light.
Right, which is important.
Absolutely. And they also give us really precise control over the wavelengths of light.
And why does that matter?
Because it helps us maximize the breakdown of that chlorine gas.
So it's all about precision and efficiency.
Exactly. And on top of all that, LEDs last way longer than traditional UV lamps.
Oh, so less maintenance too.
Yep, lower cost in the long run.
Makes sense.
Hmm.
All right, so we've got the process down, Pat. Where do we actually put this into action?
Well, remember those two scenarios we talked about?
Yeah, the landfills and coal mines, and then the larger scale atmospheric removal.
Right. So for those concentrated methane sources like landfills and coal mines, the paper proposes these small self-contained systems. They be placed right at the source.
Like little methane zapping stations.
Pretty much. And they be integrated with the existing ventilation systems to capture and neutralize any leftover chlorine before it's released.
So we're containing the methane and neutralizing the byproducts.
Exactly. 2 birds, 1 stone.
I like it. And what about the larger scale atmospheric removal?
That's where those existing chlor-alkali plants come in.
Right.
They could be adapted to produce the chlorine for this process.
Essentially becoming dual-purpose facilities.
Yeah, producing valuable chemicals and removing methane from the atmosphere.
Okay, I'm fully on board with this idea, but I have to ask about the potential downsides.
Of course.
I mean, using seawater for electrolysis generating chlorine gas, it all sounds a bit risky.
I hear you. There are definitely risks to consider, but the researchers do address some of these in the paper.
Okay, good. I was hoping they wouldn't just gloss over that.
No, they definitely don't. So, first of all, they really emphasize the importance of careful location selection.
Right, we were talking about coastal areas with alkaline soil or proximity to the ocean.
Exactly, to help neutralize that hydrochloric acid byproduct.
The acid rain prevention plan.
Precisely. And they also stress the need for thorough environmental impact studies before any large-scale deployment.
Which makes sense.
They're not suggesting we just start pumping chlorine into the atmosphere without understanding the consequences.
Good to hear they're taking a cautious approach.
Yeah, they're really focused on both the technical aspects and the environmental considerations.
So they're not just focused on the solution, but also on doing it responsibly.
Exactly. And they go beyond just addressing the risks. They've also done some initial calculations on the potential benefits.
Okay, let's hear it.
Well, as we mentioned, they estimate that this method could be cost competitive with those existing CO2 capture technologies.
That's a big deal.
It is, but here's where things get even more interesting. Remember that sodium hydroxide byproduct, well, it turns out it can be used for CO2 capture.
Wait, so we're removing methane and pulling CO2 out of the air?
Exactly. It's like a double whammy.
Wow.
And because of this, the researchers believe this technology could actually create negative emissions.
Meaning we're removing more greenhouse gases than we're emitting.
Precisely.
That's incredible. So it's not just about mitigating damage, it's about actually reversing climate change.
Exactly. And they argue that if the chlor-alkali industry were to scale up production and dedicate even a portion of its output to this, we could see significant reductions in atmospheric greenhouse gases.
So we're talking about turning an industry that's often seen as part of the problem into a key layer of the solution.
Exactly. Of course, this would require a huge shift in thinking and investment, but the researchers believe the potential payoff is worth it.
It's definitely a lot to think about. This paper has given us a lot to chew on, but I have to ask, are there any other potential downsides besides the acid rain risk?
You're right. Every solution has its trade-offs, and the researchers are very upfront about the fact that there's still a lot of work to be done to understand all the potential downsides.
Yeah, for sure.
So what are some of the big question marks they highlight?
Well, one thing they point out is the efficiency of the chlorine photolysis step.
Okay.
We need to make sure we're really effectively breaking down that chlorine gas,
Yeah.
To release all those reactive atoms.
Right.
If that part isn't working well, the whole system kind of falls apart.
They're all connected.
Exactly. But the good news is the paper mentions a startup that's already working on ways to boost the efficiency of that process.
Oh, wow. So it's not just theoretical?
Nope. People are already trying to make this happen.
That's exciting.
It is.
What other challenges do they mention?
Another big one is figuring out how to recycle the unreacted chlorine in the hydrochloric acid.
Right. We don't want those chemicals just building up in the environment.
Exactly. It would defeat the purpose of trying to be eco-friendly.
So they suggest looking into different methods for capturing and reusing those chemicals,
Okay.
which would obviously boost efficiency and minimize any environmental impact.
So it's like a closed-loop system.
Exactly.
It seems like they've really thought this through, both the potential benefits and the potential problems.
I agree, and they're not shying away from the challenges, which actually makes me more confident in their findings.
That's a good point.
They're really trying to present a balanced perspective.
I think that's what I like most about this paper.
Mm-hmm.
It's not just presenting this miracle solution.
Right.
It's really acknowledging that there are a lot of complexities and exploring all the different angles.
Yeah, and one thing that really struck me is how they connect this technology to the bigger picture of, climate change mitigation.
Right. It's not just about removing methane.
Exactly. They're talking about how it could actually contribute to reducing overall greenhouse gases.
Right. And we talked about the potential for negative emissions. Actually removing more CO2 from the atmosphere that we're putting in.
It's a huge deal.
It is. And they make a really compelling argument for the role that the chlor-alkali industry could play in all this.
Yeah. If they were to scale up production and dedicate even just a portion of their output to this, we could see a real impact on global emissions.
So we're talking about turning an industry that's often seen as part of the problem into part of the solution.
Exactly. And of course, that would require a massive shift in thinking and a lot of investment. But the researchers argue that it's worth it.
It's definitely something to think about.
It is.
This paper has given us a lot to consider. So what would you say is the key takeaway for our listeners today?
I think the biggest thing to remember is that we need to be open to these new and innovative solutions, even if they seem kind of out there at first glance.
Right.
This chlorine atom method is a perfect example of that.
Yeah, it's about thinking outside the box, challenging our assumptions, and looking at things from a different perspective.
Exactly. Who would have thought that something we use to keep our swimming pools clean could actually hold the key to tackling climate change?
It's pretty amazing.
It is. It just goes to show that sometimes the answers are right in front of us. We just need to be creative enough to see them.
Well said. Well, thank you so much for taking the time to break down this research paper with me. It's been a fascinating conversation.
My pleasure. I always enjoy these deep dives.
And to all of you listening out there, thank you for joining us on this journey of discovery. We hope you found it as thought-provoking as we did. Remember, knowledge is power, and together we can make a difference. Until next time, stay curious.